Hey guys, this is the first video for chapter 4, just finishing up the reactions that we have to talk about in the different classifications of reactions. We talked about in chapter 3 a couple of them. We talked about decomposition, synthesis, and combustion. So we're going to kind of finish up with a couple of reactions kind of like those where it's the mechanism, and then we're going to look at some product-based classifications. So the first new one that we talked about is single replacement reactions. You can see kind of the idea here where we have one element taking the place of another in the compound. You know, A replaces B in a compound, so we have an element reacting with a compound. That's kind of what we have here. We have an element reacting with this compound. So this guy has to be an element. You can see an example down here. We've got zinc reacting with hydrochloric acid to produce zinc chloride and hydrogen gas. The zinc booting the hydrogen out of this compound, taking its place and producing hydrogen gas. So that's the general idea with single replacement reactions. They're very important as far as reactions go, as we'll see at the end. One of the reasons why single replacement reactions are so important. Double replacement reactions are a little bit different. There's two ways to look at them. I like to think of the cation switching places or the anion switching places. You take the positive or negative elements or compounds and replacing them with each other. A switches with C, so A reacts with D, C reacts with B. The other way you can kind of look at it is inner and outer. So you take B and C, react them together. You take the outer elements A and D and react them together, and so you get AD plus CB. Either way to think of it, the point is that we're taking the cation and anions and reacting them with the other cations and anions, like we have here. We have sodium and sulfate, barium and chloride. So sodium and chloride, the inner ones are going to get together, barium and sulfate, and then the outer ones are going to get together, sodium and chloride, so forming barium sulfate and sodium chloride. Notice that barium sulfate is a solid, which is what we'll look at in the next video. Now, a couple of other reactions or I guess types of reactions are based off of either what they form or something like that. So the first one that I want to talk about is neutralization reactions, or otherwise called acid-base reactions. Remember the Arrhenius definition of acids we talked about: produces hydrogen in water, and for bases produces hydroxide in water. And so this is still a double replacement reaction. We take the inner ones and react them together, the cation and anion, or the cation and anion rather, and react them together to form a salt, in this case NaCl. And the outer things react together. That's the cation from the acid, which is hydrogen, the anion from the base, which is hydroxide, and that forms water. Now, the general form is an acid plus a base form a salt and water. And what do we mean by a salt? Well, we mean an ionic compound here. There we go. Okay, so a salt and water. So that's what we have here. So you can do any acids and bases. I mean, we can take some weak acids and bases, which we'll talk about which ones those are here in just the next video. But again, we just kind of take the hydrogen off of the acid, the hydroxide off of the base, and we form water. And we take whatever's left over and react the cation with the anion. So we have NH4, ammonium acetate, C2H3O2. So there's that, neutralization reactions. Acids also react with some other things to form gases. And so if you form a gas at the end, we consider that a gas-forming reaction where we actually don't start in a gaseous form. You know, we can have something like H2 plus N2 makes NH3, and all of these guys are gases. Of course, that wouldn't be a gas evolution because we're starting in the gas phase and in the gas phase, nothing's changing. But here, with these two, they're very similar. we have a carbonate or a sulfite reacting with an acid. Now, if we were to do our normal, inner and outer thing, or double replacement thing, we would form H2SO3 and H2CO3, carbonic and sulfurous acid. Now, the deal with these two guys is that they're very unstable. In fact, we'll use sulfurous acid once in the lab, and it's a kind of a big deal to leave the lid on, because you'll release the sulfur dioxide and decompose the acid even more so. So if any time you would form these two products, instead of forming carbonic acid, we form carbon dioxide and water. Okay, so it just breaks apart. You can see it's H2O and CO2. Again, same thing here. Sulfurous acid breaks into sulfur dioxide and water. Now, not all of the molecules do this, but this is the general, that if you're not containing the reaction, this is what's going to happen. So instead of maybe a bottle, you do this in a beaker. That's what's going to happen. For this guy, we still do a double replacement, but instead of decomposing anything, you just need to know that H2S is a gas. Hydrogen sulfide is a gas. And so once again, if we don't contain it and kind of force some of this gas to dissolve in water, it's going to be a gas. So that is another gas evolution. Metals reacting with acids also form a gas. This is a single replacement reaction, taking the place of hydrogen in this compound, booting hydrogen out to hydrogen gas, and so we have gas formed. So gas forming reactions are based off of their products there. And just need to have a couple things you need to remember. If you would form carbonic acid, you form carbon dioxide and water instead. If you would form sulfurous acid, you form sulfur dioxide and water instead. Hydrogen sulfide is a gas, and metals reacting with an acid form a gas as well. Now, the last one that we have to talk about is oxidation or reduction reactions, or redox reactions. So oxidation and reduction, these reactions are the reactions that involve the transfer of electrons. And they're very important reactions to us, because that's how that provides us with energy, that it has a lot of biochemical importance. But anytime you have a transfer of electrons or a change in what we call oxidation state, we have a redox reaction, which is what we have going on here. We have the copper 2+ ion coming in. Zinc gives its 2 electrons to copper. So we have a transfer of electrons there, and then we have zinc ions leave into the solution. So that's just a little basic example of a redox reaction. But we have a kind of a definition of these two terms. If something is oxidized, it loses electrons, and something is reduced, it gains electrons. So here, copper's coming in, it gains electrons, so it's reduced, and zinc is losing electrons, so it's oxidized. A couple of things that you can use to remember this is oil rig. This one I used. This is reduction is gain of electrons, and oxidation is loss of electrons. So that can help out. The other one is Leo Ger. Same type thing. Okay. Loss of electrons is oxidation. Oxidation. Gain of electrons is reduction. So you can use either one of those, but little mnemonics to help. Now, how do we know? How do we know what's oxidized and what's reduced? Well, we have these rules, and I want you to kind of just take a look at these rules very briefly, just to kind of get them down. And you may have to pause this right here and kind of read through them. But elements in their elemental form have an oxidation number of 0. The sum of the oxidation numbers in a neutral compound is 0, or if it's a charged thing, like a polyatomic ion, the sum has to be the charge. the oxidation of state of a monatomic ion, so like iron to copper to zinc, something like that, the ions, that's the same as its charge. Nonmetals tend to have negative oxidation numbers. Oxygen has a -2 state unless it's bonded to group 1 metals or group 1 elements, where we have a -1 state, or possibly -1/2. Hydrogen is -1 when it bonds to a metal, or +1 when it bonds to a nonmetal. So let's look at some examples of this. So, what is the oxidation state of each element in these compounds? Well, we know that we've got a 2- here, and we've got a 1- here for these guys. So if oxygen's 2-, and we've got a negative charge out here, so we've got 2-, 2-, 2-, that gives us a 6- total. We want 1 left over, so that means nitrogen is going to have to be a 5+. Nitrogen is going to have to be a 5+. Here we've got 4 chlorines, 1-, 1-, 1-, and 1-. That's 4 negative charges from the chlorines, meaning that phosphorus is going to have to be a 4+ for this to be a neutral compound. Here we have iron bonded to hydroxides. Now, to understand the charge here, we know hydroxide's a -1 charge, so that means that iron is going to have to be a 2+, but we can also assign oxidation numbers for each of these elements as well. Oxygen's -2, 2- because it's not in a peroxide ion. And if we look here, hydrogen is a -1 is bonded to metal, a +1 when it's bonded to a non-metal. So this time hydrogen is a +1, giving us a -1 for the hydroxide ion and a 2+ for the iron. So that's how we assign oxidation states for elements in compounds. And let's take a look at a quick example of a redox reaction where we have a transfer of electrons occurring. So here we have one of the more complicated examples of redox reaction. So let's look at assigning oxidation numbers. Here, hydrogen's bonded to a nonmetal, so this guy's got to be a +1. And so we have 4 +1s, or 4 1+s from hydrogen, or 4 +1s. We just as a rule of thumb, oxidation states are usually listed as plus, or as a symbol then number, actual ionic charges, number then symbol. And so carbon here is it has to be, in order for this to be 0, it has to be a -4. Oxygen in its elemental form, remember, elements in their elemental form have 0 oxidation state. Here, hydrogen's bonded to a nonmetal, so this has to be a +1. 2 +1s gives me a +2. Oxygen, still a -2. Here, oxygen, still a -2, because it's not in a peroxide ion. And what we mean by peroxide, something like Na2O2, we know that sodium has a +1 charge, and in this case oxygen would have a -1 charge. This is sodium peroxide. Alright, so -2, we got 2 of those, that's -4, so we have a +4 here. Carbon going from -4 for an oxidation state to a +4, and oxygen going from 0 to -2. Okay, if we look, going from 0 to -2, you have to gain 2 electrons, so that's got to be reduction. And going from a -4 to a +4, you have to lose negative charges, so you have to lose electrons, and that is oxidation. Take some practice, but there you go. And that's how we determine if something is redox reaction. Just as a real quick aside as well before we end the video, single replacement reactions are always redox reactions. Single replacement reactions are always redox reactions by definition, because we have to have an element reacting with a compound, and an element has an oxidation state of 0. See you next time where we'll talk more about Chapter 4.